Ever wondered how a jolt of electricity becomes the spin of your car's wheels? That's the magic of electric motor manufacturing, a field dedicated to transforming electrical energy into the mechanical motion that drives our world. The creation of these motors is a meticulous process, with each step offering opportunities to elevate performance. By making smart design decisions throughout, manufacturers can streamline production and ensure the highest quality motors roll off the assembly line. In today's competitive industry, every efficiency gain in an electric motor translates to a car that's faster, more reliable, and kinder to the environment. The unassuming electric motor, despite its seemingly simple function, boasts a surprisingly intricate backstory. Its creation is a journey filled with surprisingly bendable materials and steps that involve mysterious liquids. Here's the catch. Mistakes at any point in this process can snowball, creating problems further down the line that ultimately hurt the quality of the final product. To prevent these imperfections, it's crucial to understand how seemingly minor settings and how they interact with each other can have a major impact. The ever-growing demand for dependable electric motors, built to precise specifications, necessitates a manufacturing process with tight controls and a high degree of adaptability. After all, the precision maintained during various stages, from meticulously winding the coils to securely connecting parts, significantly impacts how well the machine runs. Common problems that plague electric motors during use, like overheating, electrical shorts, and bearings failing, can all be traced back to a lack of control during their creation. In essence, every smooth-running motor is a testament to the delicate balance achieved throughout the manufacturing process. Manufacturing isn't as simple as throwing things together. It's an intricate dance between strong, unyielding materials and those that can be shaped and formed. Every step, every twist and turn in the process needs to be precise. Even the slightest misstep, a setting out of whack at any point, can introduce a flaw, a weakness in the final product. To prevent these imperfections from snowballing down the production line, catching them early is key. We can't wait until the very end, when everything is assembled, to find a problem. Identifying and addressing defects as soon as possible is crucial for a smooth-running production chain and a flawless final product. The rotor's core is made of hundreds of small slices of metallic material called laminations. Each is stamped or punched and then thinly coated, a few microns, to protect from corrosion and provide better insulation. This production process, called lamination, begins when all laminations are stacked one above the other and then stamped to create the rotor's core with the help of a hydraulic stamping press. This manufacturing method is essential to build an efficient rotor. Laminations reduce eddy current inside the rotor while increasing the rotor's strength and improving its balance. The rotor shaft is now the only part missing. They select the appropriate material, typically high-grade steel, considering factors like strength, weight, and corrosion resistance. Manufactured separately, The shaft can be cleaned with a laser to remove oil, dust, or any contaminants remaining from its manufacturing. It can also be laser marked for traceability or tracking purposes. Depending on the application, the shaft may undergo heat treatment processes to improve its mechanical properties. This can involve hardening specific areas for wear resistance or tempering for overall strength and toughness. Putting in a shaft isn't a one-size-fits-all job. How it's done depends on what the shaft will be doing, but typically, you'd place the shaft very carefully inside the rotor assembly. To lock it in there just right, they might use a press to push it in really tight, or they might use heat to make everything fit together perfectly. Asynchronous motors with distributed winding account for the major share of electric motors. Unlike the concentrated winding, not every tooth pole is wound in a distributed winding. Instead, coils are in slots and span multiple pole teeth. Since the winding may block slots from further insertion of wire, it may be necessary to wind a complete phase winding at one time. Coil insertion machines insert prefabricated groups of coils into the stators of electric motors. The coil groups are frequently manufactured with flyer winding machines and put onto the insertion tool with a transfer instrument. In small batch manufacturing, the coil groups are relocated manually from the winding masks to the insertion tool using transfer instruments. Subsequently, an insertion tool places the performed winding into the stator slots. The slots are sometimes insulated with paper. When diagonally winding the coil into the slot of the stator, the coil's internal width must be larger than the stator's height, which leads to the formation of the large winding head that is characteristic for the insertion technique. After the winding is complete, the next step of the electric motor contract manufacturing process is to varnish the windings. Varnishing an electric motor winding electrically insulates the winding, makes it mechanically solid, and protects it from contamination. To sustain speeds as high as 10,000 RPMs, precise balancing is required to ensure smooth running without vibration. Mass distribution is measured by placing the rotor on a horizontal or vertical fixture equipped with measuring devices such as accelerometers, tachometers, and scales. These instruments monitor acceleration, rotation speed, and weight as the rotor spins. Adjustments are made until the balance is met. Hydroelectric turbine manufacturing is a specialized industry that deals with the production of turbines used to convert the energy of moving water into electricity. These turbines are a crucial component of hydroelectric power plants, which are a major source of renewable energy. Turbines are designed to run for decades with very little maintenance of the main elements. Overhaul intervals are on the order of several years. Maintenance of the runners and parts exposed to water include removal, inspection, and repair of worn parts. Normal wear and tear includes pitting corrosion from cavitation, fatigue cracking, and abrasion from suspended solids in the water. Steel elements are repaired by welding, usually with stainless steel rods. Damaged areas are cut or ground out, then welded back up to their original or an improved profile. Old turbine runners may have a significant amount of stainless steel added this way by the end of their lifetime. Elaborate welding procedures may be used to achieve the highest quality repairs. Other elements requiring inspection and repair during overhauls include bearings, packing box and shaft sleeves, servo motors, cooling systems for the bearings and generator coils, seal rings, wicket gate linkage elements, and all surfaces. Turbine blade materials. Given that the turbine blades in a water turbine are constantly exposed to water and dynamic forces, they need to have high corrosion resistance and strength. The most common material used in overlays on carbon steel runners in water turbines are austenitic steel alloys that have 17% to 20% chromium to increase stability of the film, which improves aqueous corrosion resistance. The chromium content in these steel alloys exceed the minimum of 12% chromium required to exhibit some atmospheric corrosion resistance. Having a higher chromium concentration in the steel alloys allows for a much longer lifespan of the turbine blades. Currently, the blades are made of martensitic stainless steels, which have high strength compared to austenitic stainless steels by a factor of 2. Along with corrosion resistance and strength, weldability and density are important criteria for turbine blade material selection. Greater weldability allows for easier and high-quality repairs. Low density allows higher efficiency and easier rotation. The most common material used in Kaplan turbine blades are stainless steel alloys. The martensitic stainless steel alloys have high strength that allow thinner sections than standard carbon steel. Reduced mass enhances the hydrodynamic flow conditions and efficiency of the water turbine. It is important to minimize erosion in order to maintain high efficiency, because erosion negatively impacts the hydraulic profile of the blades, which reduces the relative ease of rotation. Giant electric motors, more precisely generators in hydroelectric plants, are truly remarkable feats of engineering. They convert the mechanical energy of moving water into electrical energy. The process begins with meticulous design and engineering. Factors like the water flow rate, turbine characteristics, and desired power output are all taken into account to design the most efficient generator for the specific hydroelectric plant. The rotor shaft is the heart of the generator. It's a massive, cylindrical piece of steel that spins within the generator. The process of forging the shaft involves heating a steel bloom, a large block of steel, to a high temperature and then shaping it using a hydraulic press. The rotor is built around the forged shaft. Large laminations of electrical steel are stacked together to form the core. Coils of conductor are then placed around the core to create the electromagnet. At the heart of the generator lies the stator, a stalwart and unmoving structure. This behemoth, crafted from solid steel, boasts a laminated core, a layered masterpiece designed for optimal performance. Coiled within it are windings, like the innards of a giant spool. When energized, these windings hum with life, generating a powerful magnetic field. Creating these windings is no small feat. Thick copper wires, each a testament to high conductivity, are meticulously wrapped into coils, their design dictated by precise specifications. Often, specialized machines are brought in to handle this task. For these are no ordinary wires. Their size demands a masterful touch, and the machines ensure each coil maintains a consistent form. The frame, the backbone of the stator, offers unwavering support to the core and its precious windings. Depending on the generator's purpose and stature, this frame might be welded from sturdy steel plates or cast from alloys boasting immense strength. The heart is built, but the assembly is a symphony. Core, coils, and frame are brought together with meticulous care, ensuring perfect alignment and a clear path for cooling. Once this masterpiece is complete, it undergoes a rigorous test, a gauntlet to prove its worth. Performance and safety are paramount, and only those who pass with flying colors are deemed worthy. Finally, the moment arrives. The generator is commissioned, its slumber broken. It awakens to its purpose, ready to transform the power of rushing water into the lifeblood of our world, electricity. The completed motor and generator, marvels of human engineering, embark on their journey to the hydroelectric plant. Once inside the dam, a challenging task awaits. The sheer size of the turbine and the confined space within the dam demand meticulous planning and execution. Powerful cranes carefully lift the massive machinery, placing it precisely within a prepared pit. Here, meticulous workers ensure perfect alignment between the turbine shaft and the generator before securely fastening them together. The most modern installation methods are applied here because the value of these turbines is not cheap. Everything must be absolutely accurate. Every component, mechanical and electrical, undergoes rigorous inspection and testing to guarantee not only functionality but also absolute safety. Measurements are meticulously taken to confirm the turbine's power output and efficiency, ensuring they align perfectly with the design specifications. Throughout this intricate process, minimizing disruption to the surrounding ecosystem remains a top priority. Stringent safety protocols are meticulously followed during construction and installation, safeguarding both the workers and the environment they work within. Hydroelectric power plants are usually located in dams that impound rivers, thereby raising the level of the water behind the dam and creating as high a head as is feasible. The potential power that can be derived from a volume of water is directly proportional to the working head, so that a high head installation requires a smaller volume of water than a low head installation to produce an equal amount of power. In some dams, the powerhouse is constructed on one flank of the dam, part of the dam being used as a spillway over which excess water is discharged in times of flood. Where the river flows in a narrow, steep gorge, the powerhouse may be located within the dam itself. In the Artvin province of Turkey, a grand project unfolds, the Yusufeli Hydroelectric Power Project. Here, a powerful dam and a modern power plant join forces to harness the energy of the Koru River. Construction began in February of 2013, with the goal of bringing the plant online by June 2021. Once at full capacity, this marvel of engineering is expected to generate a staggering 1.888 billion kilowatt hours of electricity each year. The centerpiece of the project is a towering 275-meter-tall dam built in the double curvature concrete arch style. This titan works in tandem with a power plant housing three mighty 186 megawatt turbine units. Each turbine is designed to handle the immense pressure of a 191-meter waterhead and a flow rate of 107 cubic meters per second. The dam creates a vast reservoir stretching over 33.63 square kilometers and boasting a storage capacity of a mind-boggling 2.2 billion cubic meters of water. To ensure accessibility and integration with the surrounding environment, the project incorporates a network of 4 balanced cantilever viaducts, totaling over 2 kilometers in length. Additionally, a comprehensive network of roads, tunnels, bridges, and culverts was constructed to support the project.